Why is engine actual thermal efficiency different from ideal? Imagine you're trying to run a race with a perfect track and no obstacles. It sounds easy, but in real life, many things slow you down. Engines are the same way. They can't reach the perfect efficiency we see in textbooks. Thermal efficiency tells us how well an engine turns fuel into useful work. The ideal version, like the Carnot engine, shows us the maximum possible efficiency between two temperature points. It assumes everything is perfect, no friction, no energy lost, just smooth, reversible processes. But engines in the real world are far from perfect. One big reason for the difference is that real engines can't operate in a fully reversible way. Every process, like burning fuel or transferring heat, creates entropy, which is a fancy way of saying some energy becomes unusable. This energy loss means they can't reach the maximum efficiency predicted by theory. Friction is another factor. Moving parts like pistons and crankshafts rub against each other, consuming some of the energy produced. This mechanical loss reduces the net work the engine can do. Think of it like trying to push a heavy box across a rough floor. More effort is needed, and less gets to where you want it. Incomplete combustion also plays a role. Not all fuel burns fully in a real engine. Some fuel remains in burned or only partially burns, so less chemical energy turns into heat energy that can be converted into work. This lowers the overall efficiency. Heat losses are common too. Engines lose heat through the walls of cylinders, exhaust gases, and cooling systems. Instead of going into work, this heat escapes into the surroundings, reducing the engine's efficiency. Pressure drops during intake and exhaust are additional issues. When gases enter and leave the engine, some energy is lost in the process, which means less energy is available for useful work. Lastly, engines don't always run under ideal conditions. Changes in load, speed, and temperature affect how efficiently they operate. They can't always maintain the perfect cycle timing or temperature difference needed for maximum efficiency. All these factors mean that real engines will always fall short of the ideal efficiency. Engineers work to close this gap by designing better combustion chambers, reducing friction, and improving heat management. For example, using higher quality fuels or increasing compression ratios can boost actual efficiency, but they still can't reach the theoretical maximum. So, the main reason for the difference is that real engines face unavoidable physical and chemical losses. These losses happen because of friction, incomplete combustion, heat transfer, and operating conditions. The ideal efficiency gives us a target, but real-world limitations keep engines from reaching it.